Light velocity in transparent solid and liquid substances. When a propagated group of visible light travels through a transparent solid or liquid substance, it will strike the molecular structure, the molecules, the atoms, and the atom components, molecular components, of that transparent substance. These solid and liquid transparent substances' molecular components are surrounded by a high density of swarming Yaldons. Transparent gases under a low pressure will not have as high of a density of swarming Yaldons as a transparent solid or liquid substance. This is due to gas molecules having a larger distance between one another, so their movement is not as restricted as a solid or liquid substance. In other words, gas molecules will have a greater velocity for Vm, as seen in figure 2.4, than solid or liquid molecules. The way a propagated group of visible light travels through a transparent gas will be discussed later on in more detail, since it will be slightly different than the way propagated light travels through a transparent solid or liquid. As a propagated group of visible light strikes the surface of a transparent solid or liquid substance, the molecular components of that substance will shake a new propagated group from the opposite side of their initial strike. The new propagated group will have a greater mass than the propagated group from the initial strike, and will then strike the next adjacent molecular structure or its components and so on as it transfers through the entire transparent medium. These substances are transparent for visible light since the molecular components are able to transfer the same momentum that is delivered from the initial set of propagated strikes. The molecular structure or components which cannot transfer the same momentum from the periodic strikes of propagated groups of visible light will not be a transparent substance. Equation 2-10 will show whether or not a substance is transparent, since it depends on the relation between the natural frequency of the molecules in a substance, Fm, and the frequency of the propagated ray, when h equals 1. According to this model of Yaldon particles, the higher dense matter will harbor a higher density of the swarming Yaldons that exist between the molecular components. The average number of the swarming Yaldons that exist within the distance of 2s max, as shown in figure 2.4, per cubic meter will be known as sigma. When a propagated group of visible light strikes the first molecular component in a transparent substance, the law of conservation of momentum will apply. As the momentum of the propagated group of visible light, mg, strikes a molecular component in a transparent substance with a velocity of Vp, this will cause the molecular component to project a new propagated group of Yaldons. This new propagated group will have a momentum, mt, that is equal to mg. The new propagated group will have a different velocity, v sub t, depending on the mass of the molecular components in the transparent substance and sigma, number of Yaldons that swarm around the molecules per cubic meter. Figure 2.4, a rough diagram representing the incoming momentum mg striking an atomic component. According to figure 2.4, the inner component will receive a momentum from the incoming propagated group of Yaldons and will oscillate with a distance, span, that is equal to 2s max with a maximum velocity equal to Vm. The molecular component will have a radius that is equal to Ra and a cross-sectional area that is equal to Aa. As the molecular component is displaced, it will propagate a new group of Yaldons with a momentum that is equal to m sub t. The new propagated group will have a mass, m sub t, that is greater than the mass from the incoming propagated group, since the incoming group is traveling from a low-dense medium into a higher-dense medium. Then the velocity of this new propagated group is v sub t, will be less than the incoming group since the molecular components of a transferred substance are able to retransmit the same momentum that is received from an incoming propagated group, mg. To find the mass of the new propagated group, the cross-sectional area of the molecular component times the displacement of the molecule, 2s max, will give the volume of coverage. This volume times the density sigma will give the number of Yaldons that will be consolidated into the new propagated group. The number of Yaldons in the new propagated group times the mass of a single Yaldon, m sub y, will give the mass of the new propagated group, m sub t. After taking the derivative of the equation above, the momentum of the new propagated ray, m sub t, will be the mass m sub t times the velocity v sub t. After taking the derivative for the equation above, after substituting the value of dm sub t into the equation above, performing integration, since momentum is conserved, then, after solving for v, where mg equals mgvp, after substituting the above equation into equation 2-8, substituting the value for S max from equation 2-1 into the equation above. As one can see from equation 2-9, the velocity of light in a transparent substance, v sub t, will be intensely proportional to the mass m and the radius ra of the molecular component in the transparent medium. As a result, the larger a molecular structure is, the slower the light will be as it travels through that transparent medium. Also, the density sigma is inversely proportional to the velocity. Then the larger groups of Yaldons that are propagated from dense transparent materials will travel slower, but with more mass. This effect is seen when light travels through a diamond compared to when light travels through glass. The diamond is a more dense substance than the glass. Then the propagated groups of light that travel through a diamond will move at a slower velocity when compared to the propagated groups of light that move through the glass. The same effect applies when light leaves the highly dense transparent substance and returns to a less dense transparent medium. The molecules on the surface of the less dense transparent medium will have a less density of swarming Yaldons that surround it. Then the less dense transparent medium will transfer the propagated visible light group of Yaldons with a higher velocity but with less mass, refer to equation 2-9. This is the reason behind light regaining its original velocity as it leaves the glass and goes back into the air. Emission and absorption lines in low-pressure gases. The molecules and atoms of gases under a low pressure are surrounded by a low density of swarming Yaldons sigma. When the molecules, atoms, and atomic components in a low-pressure gas receive an external form of energy, each of those molecular components will increase the span of oscillation while maintaining its own natural frequency. The molecules in a low-pressure gas are able to freely oscillate about their rest points with a greater span than a high-pressure gas would, since high-pressure gas molecules are more constricted by the limited space between the molecules as well as the high density of swarming Yaldons between the high-pressure gas molecules. The Yaldons that swarm around the atoms and molecules will be greater as the atoms and molecules become closer together. When the density of Yaldons that swarm around the molecules becomes greater, in the case of high-pressure gases, then the increase in the density of Yaldons around the molecules sigma will cause a high gain in the momentum for the propagated groups. The opposite is also true. The density of swarming Yaldons will be lower when the atoms and molecules are further apart from each other. Then the large displacement of molecular components in a low-pressure gas, combined with the low density of swarming Yaldons, will result in a periodic ejection of propagated groups of Yaldons with a consistent momentum. This consistent momentum will produce an emission line of a single color for each molecular component in the low-pressure gas. High-pressure gases, which have a higher amount of swarming Yaldons between the molecules, will release more energy. The propagated groups of Yaldons produced by a high-pressure gas will be more massive than a low-pressure gas. If the propagated groups from a high-pressure gas were to receive more external energy, then the change in momentum would be greater than if a propagated group from a low-pressure gas were to receive more external energy. As a result, the high-pressure gas will be able to release propagated rays with a broader range of momentum when compared to a low-pressure gas. This broader range of momentum will allow the high-pressure gas to produce a fuller spectrum of color when the molecules are excited by an external source of energy. As mentioned before, all atomic components and molecules in a low-pressure gas will release a group of Yaldons with a consistent momentum, and each molecular component will emit a certain color when it receives energy from an external source. Then the colors of the emission lines will depend on the momentum produced from the natural oscillation of each atomic component and molecules in the low-pressure gas due to the fixed period and span of oscillation from the atoms and molecules. Larger elements, which have more components in their atoms, will have more emission lines produced. The emission lines are caused by every atomic component and molecule in the low-pressure gas having its own natural frequency and periodically propagating rays at a consistent momentum. This is shown in equation 2-6. When sigma has a low value, then the substance cannot produce a wide range of propagated rays. When the emission lines produced by the excited state of the low-pressure gas is passed through the same kind of low-pressure gas, but at a lower temperature, colder, the emission lines that are produced by the natural oscillation of the molecules and atoms in the excited low-pressure gas will not be shown as it passes through the cold low-pressure gas. The molecules and atoms in the cold low-pressure gas will resonate with the emission lines by having a greater displacement from their rest points. This resonance will cause the span of oscillation of the molecules and atoms in the cold low-pressure gas to become greater with every consecutive strike from the propagated groups of Yaldons in the emission lines produced by the same gas at an excited state. As the span of oscillation of the molecules and atoms in the cold low-pressure gas becomes greater, the velocity of the molecules and atoms will also increase to a point where the molecules and atoms will be forced to leave their rest points. When the molecules of the cold, low-pressure gas will not be able to propagate groups of Yaldons at the specific color which resonate with the natural oscillation of the molecules and atoms. The other propagated groups of light that do not match the natural frequency of the molecules and atoms in the cold, low-pressure gas will be able to transfer through since they do not resonate with the natural frequency of those molecules.
See equation 2.10.
This effect of resonance between the external light source and the oscillation of the atoms and molecules can be compared to the resonance between the molecules in a glass cup and a certain frequency of sound. The molecules in the glass cup will have a certain natural frequency based upon its molecular structure and shape of the cup. When an external sound wave that matches the natural frequency of the cup is applied, the resonant frequency from the sound wave causes the molecules in the glass to become displaced to a point where they can no longer maintain their position in the structure of the glass cup. As a result, the glass cup shatters. The same effect happens to the oscillation of the molecules and atoms in a cold, low-pressure gas when given an external form of light that matches the natural frequency from the oscillation of the molecules and atoms. The molecules and atoms become so displaced from their rest points, they will not be able to produce a continuous stream of propagated groups of Yaldons for that specific frequency of light. As a result, the oscillation of the molecules and atoms which resonate with that specific color becomes shattered. Following will be a diagram and formulas to show the relation between the natural frequency of a substance, Fm, and the frequency of the incoming propagated groups. The density of the swarming Yaldons between the molecules and atoms sigma, and the velocity of the molecules and atoms Vmh. Figure 2.5. A rough diagram representing the oscillation of an atom with periodic strikes from propagated groups. In the figure above, the oscillation of the atom is represented by the motion of a pendulum to make the concept of oscillation easier to understand. In order for resonance to happen, each of the propagated groups that travel with a period of Tp should strike the mass m at the position of P1, when Vmi equals 0 for max resonance. The equation for Vm sub 1 in the diagram above is a sinusoidal representation of the velocity for the mass of the atom m, with its natural frequency of m, and Vm will be the maximum velocity of that atom after the first strike from a propagated ray. The value for Vm will come from the equation 2-9. According to equation 2-9, Vp is the velocity of light in a vacuum. V will be the velocity of light in a transparent substance, and Vm will be the maximum velocity of the oscillating molecule.
The value of V sub m will be the amplitude, for the equation V sub m1 equals V sub m.
After the first strike from the incoming propagated groups, the equation below will be for the second strike from the incoming propagated groups, which will have a frequency of for n number of hits from the incoming propagated groups within a certain period of time. The equation above can be rewritten as follows. Then, after substituting the value for Vm in the equation above, after rewriting the previous equation, according to equation 210, the velocity from the oscillation of the atoms and molecules, Vm, will sharply increase as the incoming propagated strikes match the frequency of resonance. As the value of h, number of consecutive hits, increases, the maximum velocity from the oscillation of the atom and molecules will increase linearly. Within a fraction of a second, there will be numerous amounts of consecutive hits from the propagated groups. This will escalate the velocity from the oscillation of the atoms and molecules, Vmh, to a value where the atoms and molecules can no longer keep their original rest points, when the glass cup shatters by a resonance frequency. This is why cold, low-pressure gases cannot continually propagate rays at those specific frequencies of resonance, since the small value for sigma will cause the gas to radiate less energy than what was received from the incoming emission lines, see equation 2.6. As a result, the frequencies from the propagated rays which match the natural frequencies of the cold, low-pressure gas will be absorbed by that gas. The constant velocity of propagated rays. All atoms and molecules are the basic building blocks for any body in the universe, except for black holes, which were a special case, and are surrounded by swarming Yaldons.
If a body in the universe moves with a velocity vb,
then the summation of the average relevant velocity of the swarming Yaldons around the atoms and molecules of that body will be a negative value, opposite direction, for vb. When a body in the universe is not in motion, then the summation of the average relevant net velocity of the swarming Yaldons around the atoms or molecules of the body will be close to zero. Following will be a diagram to illustrate this concept. Figure 2.6, a rough diagram representing the propagated ray group maintaining its velocity, Vp. The net velocity is Vn for the atom or molecule while it is oscillating and in motion. The velocity of the moving body is Vb. When the atom moves from P1 to the position of Po, the velocity of the atom will be Vm. Since the body is in motion with a velocity of Vb, the net velocity Vn for the atom at the position of Po will be Vn equals Vm minus Vb. The final velocity of the atom will be Vf, since the whole atom will move with a velocity of Vb, the velocity of the moving body, plus the velocity of Vn. Then, figure 2.7, a rough diagram representing the propagated ray group from the opposite side also maintaining its velocity, Vp. The atom that is illustrated in figure 2.7 is contained in a body that is moving with the same velocity, speed, and direction of Vb from figure 2.6. The difference will be the direction of oscillation from P2 towards Po. The net velocity, Vn, is position Po will be Vm plus Vb, since the resultant net velocity from the swarming Yaldons around the atom will be Vb. The resultant net velocity of the swarming Yaldons will be in the same direction of the atom's movement as position Po, but the whole body, which contains the atom, is moving in the opposite direction of the net velocity. Then the final velocity of Vf of the atom at the position of Po will be, the net velocity will be, then, according to the diagrams and formulas above, the velocity of the propagated rays, velocity of the light, will be constant regardless of the velocity of the body that emits the propagated ray, source of the light. The same principle applies to a stationary light source, but the observer is in motion, according to equation 2-9, rewritten for Vp. According to the equation above, as long as the maximal velocity of the atom, Vm, remains the same, then the velocity of the propagated groups will also remain constant. These are not the only phenomena that can be explained by using Yaldon propagation. For example, the refraction, diffraction, interface, dispersion, and polarization of light, as well as many other phenomena, can be sufficiently understood using this model.